in this review, we can study one of the important technique called the alternating series test. So, alternating series test. So, we sometimes call this AST. AST. So, as the test says, it is only applicable for alternating series. So, what is it? So, what is an alternating series? So for example, if you look at this series, so 1 minus 1 half plus 2/3 minus 1/4 plus 3/7, something like that. So what you notice it, the sign change from plus to minus and then plus, like that. So you can see sign changes alternatively. That's how we call alternating series test. So so it's plus and then minus and then plus, like that is alternatively change. It doesn't matter which one you start with. You can start with minus and then plus and then minus and then plus, or whatever, but it has to change alternatively. So it's called alternating series. So what the test says, so let's write it. So I'm going to write this as a theorem. So it's called the alternating series test, or the AST, alternating series test. So we're gonna look at that kind of series. So any alternating series you can write it in this form. It's a -1 to n minus 1. That's gonna carry the sign, but I start with a plus sign here, but it doesn't matter. You can be n or n minus 1, n plus 1, something like that. Only thing is you have to change the sign. So so if you expand it, it's going to look like b1 minus b2 plus b3 minus, like that. So that's how the series looks like. So what we can do, we can look at two properties. So the first property is the limit of bn. So we can take the limit when n goes to infinity of bn. So it has to be 0. That's the first condition. So there's something that we need to think of what if it is not. So if the limit n goes to infinity bn not equal to 0, then we don't need this one. Then we're going to use the nth term test. So then by the nth term test that we did earlier, by the nth term test, the series diverge. So we're going to go for the nth term test if the limit not equal to 0. So the series diverge, everything is over. So let's say it's 0. That means we're going to go to the second condition. So what the second condition? It says that bn is decreasing. It has to be decreasing. Bn is decreasing. Okay, bn is decreasing. Bn is decreasing means bn plus 1 is smaller than bn. That's for, like, what to say, eventually. That's the best way to write it, because we don't need. So let's say for n after some n. So sometimes we call it eventually. We don't need that starting from the beginning. Okay, after some n, it should be increasing. Then what it says that then the series sigma n going from 1 to infinity, -1 n minus 1 bn converges. So this is like really interesting. So there are two conditions to satisfy. The bn has to be the limit of bn has to be 0, and the bn should be decreasing. Remember, bn means the one without the sign. Okay, so we pick the bn part. Has to be is decreasing. 0 limit is 0 and is decreasing. Then this test says it's going to converge. And we also know that the error. So if you try to kind of approximate this one by the n partial sum, so the first missing term is the absolute error of the absolute error. Okay, so that also we can write. So if you try to get this approximate the sum by Sn, it says that error is less than or equal bn plus 1. That's the first missing term, bn plus 1, because if you go up to n, the first missing term is n plus 1. So it says the error is less than the first missing term. So that is bn plus 1. Yeah, and then we also assume that the bn bn is positive, so that's assumption. Bn we normally pick as positive or 0, can be 0. Okay, good. So let's try to look at some examples. So the first example is this one. So sigma n going from 1 to infinity, negative 1 to the n, 1 over n. So in this case you can see bn is simply 1 over n, so this is an easy one. So let's take the two conditions. So the limit n goes to infinity, bn, which is the limit n goes to infinity 1 over n, which is 0. So the first test passed. So we're going to go to the second test. What's the second test? Limit n goes to infinity. So we want to check actually not the limit part. We want to check whether it is decreasing, but you can see that so then the second condition, so the second condition is we need to check whether it's decreasing, but you can see that so not that 1 over n plus 1 is less than or equal 1 over n, that we know for n greater than or equal 1. So what this means, so this says that, so that means so this implies that bn plus 1 is less than or equal bn, okay, for all n, for any n greater than or equal 1. So that means it's decreasing. So bn is decreasing, so therefore by the alternative series test, sigma n going from 1 to infinity, negative 1 to the n, 1 over n converge. So this is gonna converge. It's very simple. That's it. That's the whole argument. So let's look at another problem. And I want to tell you something. So the note is, we know that even though this is the case, sigma n going from 1 to infinity 1 over n diverges. Okay, so diverges. So this is the harmonic series. Okay, good. So let's look at another example. So how about this one? So let's say sigma n going from 1 to infinity, negative 1 n, for n over 5n minus 1. So if you look at this problem, you can see bn is, in this problem bn is, if you ignore the sign, 4n over 5n minus 1. So we take the limit when n goes to infinity of bn. So it's the limit n goes to infinity 4n over 5n minus 1, and you can see that you only need to look at the dominating terms. So if you look at the dominating terms, 4n over 5n, that means 4/5, which is not equal to 0. So by the nth term test, series diverge. So by the nth term test, the series diverges. It's very easy, because you don't want to do anything here, because you see that the series diverge. So that's it. So let's look at one more example. We do like two more. So what about this one? So let's see sigma n going from 1 to infinity, negative 1 n minus 1 log n over n. But you know that when you have log n over n without the sign, that's going to diverge. We showed that in a previous review. So what we're going to do here is we're going to study this one. So first notice, so we have bn in this case is ln n over n. So we're going to look at the first condition, the limit n goes to infinity bn, is the limit n goes to infinity ln of n, but you can see that ln of n, ln goes to infinity, n goes to infinity. So this is the L'Hopital's problem. So we're gonna take the derivative, but remember these n are discrete, but we can assume that those are continuous variables. So we can just take the derivative, but you wanna know what you are doing. Okay, so just assume n is a continuous variable, so you can take the derivative. So it's the limit. If you take the derivative of that, so it's a 1 over n, and then this is 1. So that means this is equals to limit n goes to infinity 1 over n, which is 0. So the first test passed, and then we're gonna go to the second test. So for the second test, we wanna show that this is decreasing. Okay, so we're gonna show that bn is decreasing. So what we're gonna do again? So we have to take the. So I mean, this is not like really easy to show that bn plus 1 is less than or equal to bn by direct method. So what we try and do, we're going to use calculus here, like derivative properties. So what we're going to do, we're going to say let fx equal the corresponding function ln x over x. So that means, so if you take the derivative using the quotient rule, so it is so what's the quotient rule again? So the quotient rule is when you have u over v, the derivative is v u prime u v prime over v squared. So we can use that here. So that means x, derivative of ln x is 1 over x minus ln x, derivative of x is 1 over x squared. That's what you get. And this is easy to simplify, so you can simplify this. You can get 1 minus ln x over x squared. But you know that about the log function is increasing. We know the shape of the log graph, so it's gonna go like this. So you can see that at one point it has to equal to 1, so it equals to 1 at exactly at e is roughly 2.718. so that's a graph of log. So that means if x is bigger than e, this is gonna be negative. So this is gonna be negative. It's going to be negative if x is bigger than e. So that means if x is, let's say, 3 or more, it's going to be negative. So that means the function is decreasing. So in that case, so what's going to happen? So you can see that so thus you can say the corresponding function bn is decreasing. Bn is decreasing for, we can say, n greater than or equal 3, because e is 2.7. Okay, so therefore therefore by the alternating series test, sigma an converges. Okay, so it's not that bad. It's a simple argument. So let's do the last one. So this is the last one. How about this one? Sigma n going from 1 to infinity, negative 1 to the n minus 1 over n squared plus 3. So in this problem, bn is n over n squared plus 3. I'm going to make a different argument here. You know that we are going to take the limit when n goes to infinity. So that means for large n, that means we say like that, that means asymptotically for large n, it's going to look like n over n square. Oh, this is simply 1 over n. So it looks like 1 over n for large n, but that function has all those nice properties. So the limit goes to 0 and it's also a decreasing function. Okay, so so this one is decreasing. So decreasing. Okay, so that means for large n, this function is almost looks like that function. So that means we can, so that's another way to argue, but make sure you write this. Okay, for large n. So this one say, so you have to say for large n, we have to write that. If you say for large n, that means we consider larger values, not for small values. For larger values, bn almost looks like 1 over n. Okay, so then we're going to use that property. So that means the limit n goes to infinity, Bn, which is limit n goes to infinity n over n squared plus 3. Now if you look at the dominating term, as we argue, it is almost looks like 1 so it is 0, so the first test passed. Or you can just use the calculus as before, take the derivatives, so we can do that, but not for this one, the second part. Now we know that Bn, we can say behaves, so this is like argument, okay, behaves as 1 over n for large n, for large n. So thus Bn is decreasing. Okay, so we have all those nice properties. So and then so by the alternating series test, the series converges. Okay, so this is like another nice argument. So I hope this will help you to do problems like this. Okay, so this is the end of alternating series test review.